tag so that the user knows where all of the tools are at all times, so they cannot suffer foreign object degree damage based on tools.
Just a recap of the testing we did last semester. We had a preliminary test where we tested to see if we can actually cut the socket, since the hard chrome coating, you can see the shiny part, may have caused a concern for us. Once we realized that we could cut that, no problem, we went and tried different types of cutting, basically side milling and plunge cutting. As you can see, the plunge cutting's here, the side milling here. From there, we decided that side milling was the easiest on the end mill and the easiest to do. So we decided to go ahead with that, and then we started doing our surface finish testing. The first test that we did, Habco thought that we were too smooth, so we adopted a second pass technique, which roughens the surface, as you can see on the optical comparator, so that it allows an area for the adhesive to bind to the socket. And then our final test was our force testing using a V-block and a force transducer, finding the peak cutting forces.
So moving on to the machine design, we purchased a Harbor Freight Central Machinery mini vertical milling and drilling machine. Habco has the same machine in their facility. We performed tests to make sure it was adequate for our required feeds and speeds, and it was, so we purchased one. And we're going to automate it and heavily modify it with PLC components.
So after deciding that we were going to use the Harbor Freight machine, we decided to go ahead and do preliminary CAD on the machine to kind of start putting things together. And our first major hurdle was picking out a drive motor for the axis. Now our original selection was a AC motor, and as you see here, it was quite large as compared to the machine. So we decided that would not work for us, and we had to look at other options. So we decided to switch to an AC servo motor. As you can see here, it's much smaller, but still delivers the proper power and RPM requirements of the machine.
So the advantage of the servo motor is consistent health. It was obviously much smaller, 3 inches by 5 inches, it's much better machine. It has the same power and RPM capability, and the advantage of that is the servo motor has full torque at 0 RPM, so from 0 all the way up to our 10 RPM, full torque. We don't have to do gear reduction in the machine. We originally planned to run a 2-to-1 gear ratio for the AC motor, no longer necessary with the servo motor. Servo motor also has feedback, so tell where the machine is at all times. Also has feedback for force, how much amperage it's using, which simplifies our go home command. So when you go home, you tell the machine, go back to 0, 0, and it'll know where it wants to go. Also, with low inertia motor, we were concerned with a large motor starting and stopping that would have run out time, speed up, slow down. Because it's a low inertia motor, we won't worry about that. The motor sizing, for our table, every 16 revolutions is 1 inch of linear travel. So running a 1-to-1 ratio for our first pass at 20 inches per minute, it would be at 320 RPM. And for our second pass at 100 inches per minute, it would be 1600 RPM, which is well within the capabilities of this motor. Also, the motor we picked is a 750 watt 3-phase AC servo motor. Belt and pulley sizing, using a website, we found the belt sizing tables and equations for sizing a belt. The belt we picked is a 3/4 inch wide L series timing belt, as you can see here on the right. It's a timing belt with teeth in it. So the advantage of the teeth is that you don't need a hydraulic pulley to maintain tension. You can run it at a lower tension. Also, because our machine is so sensitive to where it is, the teeth they reduce the chance of slipping, so the machine will always be on point.
Here's the final part assembly of what we've come up with for the machine. Here's the spindle assembly that we were reusing from the old machine and the base that we were also reusing. Now here is the y-axis that will be moving back and forth for our first and secondary passes. This is the x-axis cable that will be moving across, making the actual cut. On top of that, we have the V-block, which clamps the socket up against this plate, allowing for the depth of cut to be exactly the same no matter what size socket we put in. Controlling the V-block is an air cylinder with a spring return, and controlling the y-axis is a dual acting cylinder.
Slide would have been a little more effective with a couple of annotations. Work through it.
All right, and then on the back side is just our AC servo motor mounted to a slidable plate, which allows ease of putting the timing belt on and adjusting the tension to specified.
How did you size the belt?
We use those equations. The belt torque we found is capable of supporting up to 1 horsepower. Our motor is, 1.2 horsepower. Our motor is a 1 horsepower motor, which is already oversized for our machine. We're estimating about half horsepower max that we're going to be required to use.
that based off some of your initial force calculations?
Yes.
Force measurements you took earlier in Smith?
And RPM. So moving on to the cutting deck, this is the top part that accepts the socket. In our original design that we came up with, we used a T-fitting sliding slot, and at the time, we thought it worked great. The issue we ran into, which we didn't consider, was chip buildup. In this model, or in this design, chips can build up in the channel, which can block the mobility of the machine, it can jam it up, it can break the machine. So we moved on to using a dovetail type design, where there's no spaces, or there's no holes for the chips to get sunk down into. So as the machine operates, the dovetail will push the chips out of the way. Also, to combat this problem, we'll be installing air nozzles to blow the chips out of the way as the machine runs.
Okay, here's just another view of the cutting deck and G-block assembly. As you can see, Andrew pointed out before that we have the dovetails now cut into this. Here we installed springs to help return the socket back to a neutral position so that it's easier for the operator to remove the socket and replace a new one on there. We added a way cover and screw cover to allow for covering the ways and screws to make sure that chips do not get in there when it's in its zero position and the cut begins. And this is the back side where this is the screw nut and the other side.
So manually, what would happen there is the operator drops the
Right, so the operator drops the socket on, presses the start button, and the machine automates, does what it has to do, finishes the cycle, and then the V-block releases back to this position, and the springs help assist this back into its center position, and the operator removes the cut socket and replaces with a fresh
Is there
socket.
anything that in that position that keeps the socket from falling over?
Yes,
Is it-
there,
Okay.
yeah, if you go back 2 slides, right? Oh, that one. It's actually
Got
has
it.
the
Okay.
D10 more than the socket.
Okay, thank you.
Are you integrating a safety so it doesn't operate if it's open, for
Yes,
example?
yes, we have safeties.
In order to find the appropriate size for this air cylinder, we conducted a force transducer test, and found that in the Z direction, which is in the clamp closing direction, only requires 15 pounds of force. This occurs during the first pass, or the 55 thousandths depth cut pass. And that's how we selected the size and load that is required of our air cylinder there.
As you can see, these are some of the parts that we decided to reuse. On the left picture, we have the spindle at the top. The Y-axis is on the left, and then the base. And the driving screw is on the right. And then on the picture on the right is basically how it's going to be assembled without our parts manufactured, of course.
Moving forward, after we assembled the machine, and the machine, there's obviously automation of the machine. We're doing this using the PLC. There's 2 basic inputs. There's pneumatic inputs and electrical inputs. On the pneumatic side of things, there's moving it in the X direction, there's moving it in the Z direction, and then the X direction, I believe, Y direction. Basically clamping the socket in, and as well as pulling it back to a 55 thousandths depth cut, as well as pushing it forward to a 60,000 full finish depth cut. On the electrical side of things, there's 2 limit switches to know where the machine is, as well as a start button, an emergency stop button, a find home button, and this is the basic procedure. Basically, machine starts, it clamps the V block, it starts the spindle at 2,500 RPM, pulls the spindle back to a 55 thousandths inch cut, jogs the table at 20 inches per minute, then it hits the first limit switch, stops the table, pushes the spindle forward to the full 60 thousandths inch depth, and then runs it back at 100 inches per minute, and then it stops the table, stops the spindle, and unclamps the V-block. The user can take that finished socket out and put a new one in, and deliver multiple sockets per minute.
So you get the surface finish by taking a lighter cut at higher RPM?
Yes. That was described in the second presentation, but essentially the socket has a base that looks like, or the end mill has a base that looks like this. That's a 5 thousandths difference in height. So we're actually using the teeth of the end mill to kind of scrape along and build ridges.
And deliver a repeatable rough surface, which is hard to do.
So moving on to electrical, our spindle is 120 volt single phase AC, same as a regular wall socket. Our PLC control will be using a DC power supply running 24 volts DC. This is going to run our relays, our PLC inputs and outputs. Our servo motor is 120 volt 3-phase AC. On the right is a block diagram of our electrical schematic. It shows the basic layout, but right now we're currently working with Pete to have code to get official schematic done for electrical. Excellent. On to the pneumatic, here's a pneumatic diagram. Shop air comes in at 100 to, or 80 to 100 psi. Our machine is regulated to 50. On the right is our pneumatic schematic. Shop air comes in, goes through a regular filter assembly, into a T-fitting. One end goes into the vice solenoid, clamps the vice. Other end goes into a double acting solenoid, either 55,000 or 60,000 step together. So Automation Direct is the company we're going to be ordering all of our PLC stuff from, motors, everything. It's about $2,000 for equipment. So we had the idea to contact them, say they discount such a large order. So Pete Hapco, he contacted them and told them our project is, how much we're ordering. And they replied very enthusiastically. They said they would donate all of the materials, and they would also like to put us in the magazine, the Automation Notebook. So we technically have 2 sponsors now.
Good.
So next thing.
Can you send me a check?
Basically, moving forward, this is our schedule for the next 2 months and a week. In the beginning here, we just need to finish up our electrical schematic with Pete, and then move on to making our engineering drawings for the machining, as well as order PLC components and order major components such as the base plate, control box, pulleys, belt, hardware. Then we're obviously going to machine the components or the raw materials that we've ordered at UCONN, and then assemble it. And then once we've assembled that, we're going to bring that to Hapco and do the setup with the PLC field devices, with the pneumatics wiring, all the wiring connections of the PLC, and in between here, just add PLC components to the model, obviously code the PLC over time, and assemble the part of UCONN, and then validate the machine. Once the thing is completely assembled at Hapco, we can come back and validate the machine and make sure that it completely works, and then paint the machine, and then down day, poster, and report over the last few weeks. Moving forward, this is our risk assessment. Our first risk is learning and coding the PLC, implementing the PLC, and doing the fine coding, fine tuning of it. We gave that an 8, with a fairly likely chance that we're going to come across this problem, but we have a great person, Pete, to help us through it, and I'll go into detail on that next slide. And then the next risk that we came across is breaking the machine. So basically that would set us behind a lot if something on the machine broke in an inappropriate place.
Now, you show that as being likely. What mitigation tasks do you take to try to prevent that from happening?
That's a good, that's
That
solid.
would discuss
Yeah.
it.
Okay.
And then third risk is painting the machine. That's more to do with schedule, basically everything leading up to the painting machine. Painting machine is the last in the list. So we need to just get through this schedule and paint this machine. And then failure on demo day is obviously another concern of ours, but on the next slide I'll refer to again, is that just through validation and testing and making sure that our machine is working properly and our code works, we will deliver a great machine for demo day. To mitigate the PLC training risk, obviously I just said we're going to work with Pete very closely. This Friday we already have a meeting with him for multiple hours. Breaking the machine, we're going to use either shear pins or code into the servo motor. If we exceed a certain load, it'll automatically stop. Or on the other hand, things we can just have our machine with no end mill first. So we can test it without an end mill, make sure it works completely, and then move forward. Painting is just working with Hapco, making sure the machine schedule is on time, powering through everything, and then failure on demo day, like I said before, is validating everything, making sure everything works with some of these things. That's about it. Anyone has any-
Use your clickers, please. Comments, questions?
Are you, with each socket that you're doing, you're only doing sockets, correct?
Yes.
And if you're only doing sockets, are you doing creation drive sockets, package drive sockets?
Create stress size.
So it's specifically one.
Well, okay, so it's 3/8 drive sockets, but it's every size available in 3/8 drives, including deep and shallow sockets, and everything from 8 millimeter to 40.
Yeah, you're just work, so you don't have to worry about changing the actual drive.
No, it's good.
Or the height, right? Because
For the height, because Hapco has specified a height from the bottom of the socket that is required for the cut to date. So we worked that into the model so it's the same page.
Okay, so you're not having to vary that.
No.
Okay. All right.
Why is it so critical?
That's the last thing on our list, so if we get to that, we have to do everything else.
Have you guys tried to make any assessment on end mill wear, and how many of these sockets you think you can cut before?
Yes, we have preliminary data to prove that we're gonna have a good amount of sockets be able to cut. The last batch that we did, we made 17 cuts, and the end mill virtually looked brand new.
Okay.
Just minor scuffing of the.
Are you monitoring torque, or are you monitoring any load feedback that might?
No,
somehow-
this was done on the Bridgeport in the
Okay.
machine shop, so it's not.
But I mean, facility in the machine you're building here, you're gonna try to monitor torque to get a sense as to when the end mill needs to get changed?
I think that's just gonna be up to the user to decide that, well,
Okay.
this cut didn't look too good, we should probably replace the end mill.
Okay. Any comments? Okay. All right, I look forward to see this. What color are you gonna paint it, by the way?
Go red.
All right, nice job, guys. Keep going.